Hello class, welcome to today's lesson. We're going to continue with the lesson 1 for the topic number 3, which is about distance between 2 points, areas, volumes, and some angles. And we're going to talk in this lesson again about the distance between 2 points and some other concepts related to this idea. Okay, what do we have to do today? We're going to go over these four little things in here. Number 1, what similar triangles are. Number 2, we're going to talk about the Thales theorem that probably you already know. Number 3, we're going to solve this problem, which is finding the midpoint of 2 points. It's a very common problem in mathematics and in geometry, and we're going to solve it today by analysis. And number 4, we're going to extend all our previous concepts and formulas 4 points in space, because if you notice, I have only made reference to points in the plane. Okay, for example, we have x and y. This is what we call the Cartesian plane or the Cartesian system in 2 dimensions only, and we have played with points on the plane. Okay, this is a plane, but we can also do that for points in space. Okay, we can play with points in space. I don't know if you have seen this drawing. Okay, goes like this. This is what is known as a Cartesian system in 3 dimensions. Okay, it's basically an extension of this idea into 3 dimensions with height, so to speak. Okay, you may think of this as your usual plane xy. Can you see it here? But with an added height in order to talk about space. And we're going to extend the previous concepts and formulas so that we can now work in space. It's really not complex. The extension is actually very natural. Okay, so let's start. Number 1, similar triangles. What are similar triangles, guys? Similar triangles are this. It's a very simple concept. I don't need to write any definition because anyways, we tend to forget the definitions, right? We get the main concept, but not the definition. So similar triangles are this. If I give you 2 triangles, and if those triangles happen to have the same angles, okay, the same exact angles, for example, this angle, I'm gonna call it angle 1. It's normally put in this way, which is the same as this. These 2 angles are the same. This angle and this angle are the same, and I'm labeling them as angle 2. And this angle and this angle are the same, angle 3. Then what I'm saying, or what I can say, is that these 2 triangles are similar triangles. Similar triangles. Okay, that's the basic idea, guys. It's a very simple idea. Let me give you another example. What about a very slim? Well, let me draw it better. What if we have this triangle, and we have another version in here, another triangle, and if I know that this angle is equal to this angle, and this angle is equal to this angle, and this angle is equal to this angle, then these 2 triangles are similar. Now, by the way, don't think that you're always gonna be given these triangles like in the same let's say in the same perspective or the same orientation. Okay, like you know, they look in the same direction, so to speak. No. For example, if I draw this other triangle here, okay, and if I know that this triangle has for example, this angle is the same as this, and this angle is the same as this, and this one is the same as this, then these two are also similar. All of these are similar between themselves, okay? So don't think that they're always gonna be giving you the triangles in a very pretty way, so to speak, like so or like so. They can be oriented in many ways, and sometimes it's difficult to uh, see them in your mind, okay? To see the relationships, but you have to get used to that. So what are similar triangles? Triangles that have the same angles. That's it. You can think of them as either reduced versions, like if you think of this as your reference, then a reduced version of this triangle, a smaller size, will be a similar triangle. Or if you take as reference this, then an amplification of this original triangle would also be a similar triangle. And that's all it is. It's a very simple concept. So always understand the concept. The definition comes later. The definition is just putting into very formal words the concept. But the concept is the most important thing. Okay, second thing, Thales theorem. Thales theorem. What does this theorem say? It can be established in the following way. The Thales theorem says the following. For similar triangles, and only for similar triangles, okay, I'm making this assumption. For similar triangles, the sides about the equal angles are proportional. There you go. In here, the keywords are for similar triangles. Okay, this is my hypothesis. I have to have, in order to apply this theorem, I have to be talking about similar triangles. Okay, if I don't have two triangles that are similar, okay, if this is not similar to this, then I cannot apply what's coming next. Okay, I have to have similar triangles and proportional. Okay, these two things are probably the most important things in here. So let me explain to you what this means. Again, it's a very intuitive and very simple idea. So let me draw two similar triangles. First of all, I'm gonna try my best. You have to understand that when a mathematician draws shapes and diagrams and sketches and so on, uh, we're not being very precise, okay? If I tell you that these two triangles are similar, then so they are, even if they don't look similar, okay? In this case, they look so because I'm trying to make a good effort. But if I tell you that this triangle and this triangle are similar, then they are, or if these two triangles are similar, then they are. If I tell you this is equal to this is equal to this, and this is equal to this, then by definition they are similar triangles. Even if they don't look similar, you have to understand that. That's very important. These are just drawings for reference, okay, for in order to have something to work in the mind. That's very important for you to understand. People get very confused about that. For example, also with this, if I give you a segment of line, this segment of line, and I tell you, consider the midpoint of this segment, and I draw it right there, okay? Most people, 99% of people, are gonna tell me, hey, wait, this is not the midpoint, you see? But it doesn't matter, okay? I don't have to be like very precise. If I tell you that this point P is the midpoint of this segment, then so it is. So it is because I'm telling you so, okay? You see what I mean? Because I'm telling you so. It doesn't have to look good, or it doesn't have to look as though it really is the middle point over here, okay? That's very important for you to understand. That's a source of much confusion. Okay, so let's go back. Mm, we have two similar triangles by hypothesis, and so that means that the angles are equal, all the angles are equal, angle 1, angle 2 equal, and angle 3 and angle 3 are equal. Perfect. So we have two similar triangles. Then what this theorem tells me, a very important theorem in geometry, in classical geometry, tells me the following, that the sides about the equal angles are proportional. What does that mean? Let me give names to the sides. I'm gonna call this side A, this side B, and this side C. And usually when you talk about similar triangles, you want to do something like this. I'm gonna call this side, which is the corresponding side to this one, you see? I'm gonna call it the same, but with a little thingy in here that it's called prime, A prime, B prime, and C prime. This is very usual in mathematics. Okay, so this little symbol is called prime. And the theorem says the following. The sides above the equal angles are proportional. For example, consider the angle 1, this angle 1. I can make two proportions with regards to the sides. I can do the following. B is to B prime as A is to A prime. Okay, in other words, the ratio between B and B prime is the same as the ratio between A and A prime. And in mathematical formulation, this means the following. B is to B prime as A is to A prime. There you go. That's what the theorem says, guys. Okay? And I'm making reference to the angle 1. I'm working with the sides about. That's what about means. The sides about the equal angles. In this case, my equal angles are this one, and these two sides, are the sides about the equal angles. Okay, now this I can also produce another ratio. Okay, I can also say this: B is to A as B prime is to A prime. So we can write this: B is to A as B prime is to A prime. So I can also produce this ratio. And that's it, guys. That's all the Thales theorem is saying. Okay, basically they're telling us that the sides about the equal angles are proportional. And that proportionality is established through equations like this. Okay, and you have to consider the same angle, just like I did. Let me consider, for example, the angle number 2, so that you can see what I mean. If I did the same, but now with regards to the angle number 2, then I can produce two ratios. I can either say B is to B prime, let's write that, B is to B prime as C is to C prime. Okay, this is one of the ratios that I can produce. Or another way to say the same is this: B is to C, as B prime is to C prime. There you go. Okay, perfect. So either way, either of these two ratios, either of these two equations work perfectly. And in fact, as an exercise, I'm going to ask you to demonstrate that these two things, these two equations, remember, it's a good idea to label the equations. Equation 1 and equation 2 are in fact equivalent. You can get the 2 out of the equation 1 or vice versa. These two things are completely equivalent, and it's very simple to show how. Okay, so that's what the Thales theorem says. Are we going to prove it? No. Okay, I cannot be proving everything because that takes a lot of time. It's a lot of fun, but it's a lot of time. If you want, try to look up the demonstration. And let's continue. Okay, why am I talking about similar triangles and the Thales theorem? Why did I touch upon these two things? Because I need them in order to solve today's important problem, which is this, okay, this problem right here. This is what we want to know today, which is find the midpoint of 2 points. What does that mean? It means the following. Suppose I give you, one more time, the Cartesian plane, and I'm going to give you 2 points, point 1 and point 2. Point 1 has coordinates x1, y1. Point 2 has coordinates x2, y2. And let's join them through a segment of line. There you go, more or less. Okay. Another thing that you need to understand, guys, is the following. This is a segment that joins P1 and P2. You don't call this the distance, okay? What is the distance? The distance is the length of this segment, okay? La longitud de este segmento es la distancia. But those are two different concepts. One thing is the geometrical object, which is known as the segment, and the length, the numerical length of this segment is what we know as the distance. Mathematically speaking, are two different objects, distance and segment. Okay, so we have these 2 points, and I ask you to solve the following problem, which is find me the coordinates of the point that divides this segment that joins P1 and P2 at the midpoint, or that divides this segment in two, which is this, okay? So this point is called the midpoint of the segment, or the midpoint of P1 and P2. More properly speaking, it should be called the midpoint of this segment. Okay, and let me call it PM. M for middle point. And I'm gonna say that PM has coordinates xm, comma, ym, and my task is to find these two coordinates, xm and ym, the coordinates of the midpoint, if I know x1, y1, x2, and y2. We are supposed to know these 4 coordinates, and our task is getting to know these 2. Okay, how do we do it? We're going to do something similar than yesterday in the class before, in which we drew some parallel lines. This is parallel to the y-axis, and this one is also parallel to the y-axis. Or you can say that these 2 are perpendicular to the x-axis. Both things are the same, right? And I'm also going to drop a perpendicular to the x-axis from this point. I'm going to drop a perpendicular to the x-axis. Perfect. And then I'm going to draw this. I'm going to draw a perpendicular to the y-axis from this point up until it touches this segment. There you go. So we're going to create this figure, okay, which is very similar to what we did in the class before. And we're going to make use of the Thales theorem, which makes use of similar triangles in order to solve this problem. Okay, here we go. Okay, what do we do? If you notice, guys, by doing this arrangement of parallel and perpendiculars and so on, one more time we have created one triangle, one large triangle, which I'm tracing right now. Okay, this large triangle, you see, and this little triangle here. Okay, large triangle, small triangle. And we can show right now that these 2 triangles, the large one and the small one, are in fact similar triangles. They are similar. Let me first disjoin them. Okay, I'm gonna like take them apart and put them in here. I'm gonna do that first. I'm gonna take this one and I'm gonna put it here. It's not a necessity, but I think it shows the demonstration in a clearer way. And I'm gonna take the large one. I'm gonna put it over here. Okay, there you go, more or less. And you have to notice the following. First of all, both triangles have right angles. This is a right angle, right? Because this and this are perpendicular, And the same goes for this. This is a right angle. So this angle and this angle are the same. You see? So we have already one angle that are the same in both triangles. Perfect. Now, this angle in here, which I may call angle 1, is the same for both of them, given the geometrical disposition of both triangles. This is the same for both. So, okay, it's the same for both. So we have one equal angle, which is the right angle, another equal angle, which is the angle number 1, and by deduction, we have to agree that this and this is also the same. They have to be the same. Okay? They have to be the same. Why? Why though? If two triangles have two angles that are equal, like in this case, this is equal to this and this is equal to this, then why? That's enough to say that the remaining angle will be equal. Why? This is going to be an exercise in the workbook. You're going to demonstrate why this has to be the same. It's very simple. Okay, so we have shown, well, you're going to show in a moment in the workbook that these two things are also the same, these two angles, and therefore we have concluded that these two triangles are similar triangles. Perfect. And when we have similar triangles, I can make use of the Thales theorem. Okay, and only for similar triangles I can use the Thales theorem. So let's use it. I'm gonna keep working with white. I'm gonna erase this and pay attention. This is the most important part of the demonstration. If you notice, guys, these 3 points right here, this one, and this one, this is x1, this one is x2, and this one is xm. For the very similar reasons that we talked in the last class. Okay, these 3 things are very easy to understand. x1, this is xm, and this is x2. So tell me, what's going to be the length of the side of this triangle, which is this one, okay, this little side. We know that this is xm, we know that this is x1, so clearly this length of these cathetas will be xm minus x1. I hope you can see that. And if not, pause the video and make sure. Okay, this thing is xm minus x1. Perfect. And similarly, the length of these cathetas of the large triangle is x2 minus x1. There you go. Okay, so we have everything prepared, all the ingredients are already put in place in order to try to get first one of the coordinates. In this case, this one. I'm gonna get first xm. Okay, so how it works? How does it work? I'm gonna apply the Thales theorem. What does the Thales theorem say? For similar triangles, are they similar? Yes. So for similar triangles, the sides about the equal angles are proportional. And let me choose this angle 1. Okay, so this side is to this side, which I'm gonna write right now. This side is to this side, as this side is to this side. But you should agree, guys, that the ratio between this side and this side is the same as the ratio of 1 to 2. Why though? Why is this half of this? Why is the ratio between this and this the same as 1 over 2? Well, by definition, because if this is the midpoint, if this point is the midpoint of this segment, that means that the distance from here to here is half of the distance from here to here. In other words, the whole distance of this segment is twice the distance from here to here. So that's why That's why the ratio of this little side to the large side is the same as 1 to 2, or 1 2 1 over 2, sorry. And that's it, guys. That's it. If you notice, we have an equation, and what is my only variable? It's xm, because I know x1 and x2, and all we need to do now is uh, handle it. I'm gonna erase these two things. I don't need them anymore, and I'm gonna work with this equation here. I'm gonna put it back here, and now all I need to do is isolate xm, and by doing so I'm gonna be able to calculate it. So let's do it. We'll multiply both sides by this denominator, and I'm gonna get the following. And then I multiply this fraction times this, and I'm gonna get this. Okay, then I just add x1 in both sides, and I'm done. You see, I'm done. I already know how to calculate the x-coordinate of my middle point. You see, given that I know x1 and x2, because I know x1 and x2, so therefore I can calculate it. Perfect, we are done. Now there's some little neat trick in order to put this formula in a more aesthetic way, in a much beautiful way, which is like this. It's very cool. Okay, so what you do is this, guys. You go xm equals, you're gonna keep this fraction, you're gonna write this as 2x1 over 2. It's the same, right? This and this is the same, clearly. And why did I do that? So I can now perform this addition of this fraction plus this number, because now they have common denominators. So I'm gonna get, oops, I'm gonna get x2 minus x1 plus 2x1, all of that over 2, and then we have minus x1 plus 2x1, that's gonna be x1, right? This and this, all of these things will be x1, and finally we will get x1 plus x2 over 2. That's it. Let me put that in yellow over here. xm equals x1 plus x2 over 2. This is the formula for the middle point. I'm sorry, for the x coordinate of my middle point. There you have it. It's basically, guys, you can see that it's the average of the coordinates of the x coordinates, is the average of the x coordinates of P1 and P2. And by doing something similar that I did, we can get that the y coordinate of the middle point will also be y1 plus y2 over 2. Okay, but I'm not gonna do that. It's gonna be the same. It's gonna be the same analysis, but in taking in reference the y-axis. So there you go. This is the formula to get the coordinates of the middle point of 2 points. So problem solved. Okay, and now, guys, the only thing that remains to be talked about very quickly, because I don't want to extend this lesson that much. I'm gonna erase. Please write these two things down. And let's talk very briefly. Well, I'm going to erase the whole thing now. Let's talk very briefly about the extension of these concepts. All of these concepts and ideas and formulas, we have discovered two formulas, right? The formula for the distance between 2 points, and the formula for getting the coordinates of the midpoint or the middle point between 2 points, which is the thing that I just did. Okay, so now what happens when I want to play in space? What happens when now I have something like this? I mean, in reality, we live in 3 dimensions, right? We don't live in the plane. So for most applied cases, for most applied problems, we need the 3-dimensional Cartesian system, which looks like this. Okay, let me give you very quickly 2 points. Point 1, 2, 3, 2, 3, 4. We're gonna need another coordinate for representing the height of that point along the z-axis. And point 2, let's talk about, let's write 3 minus 2 minus 2. Okay, let me first tell you how you can draw these points in the space, how you can draw them. Okay, first I'm gonna draw P1. I'm gonna use, well, first I need to 1, 2, 3, 4, 5. I need to write 1, 2, 3, 4, 5, 2, 3, 4, 5. I need to write my scale, right, to draw it. Okay, and what you do next is the following. So the x coordinate is 2, the y coordinate is 3, and the z coordinate is 4 of this point. So let's draw it. Let's locate point 1. So x coordinate 2. If you notice, the positive coordinates of x, or the positive values, go in this direction. So I'm gonna advance 2 units. 1, this color, well, in this thickness. 1 unit, 2 units. Okay, right now I'm right here. 2 units in the positive direction because it's a positive number. Now 3 for y, and that means a translation of 3 units in the y-axis, in the positive y-axis, which goes in this direction. So 1 unit, 2 units, 3 units, more or less. Okay, you don't have to be very precise. So 2 units in this direction, 3 units in this direction, and then 4 units in the z direction, in the positive z direction. So we go 1 unit, 2 units, 3, 4, more or less. It's just an approximation. So this point would be point 1, and that's how you draw it. 2, 3, 4, 2, 3, 4. 2 units plus 3 units plus 4 units in those specific directions. Now let me drop P2 so you understand how it works with negative coordinates. It's going to be something very similar. Let me do that in red. So first, 3 units in the x-axis. So here we go. 1, 2, 3. We are right here right now. And then minus 2 units in the y-axis. The negative units run in this direction to the left, so to speak. So I'm right here, and I'm gonna go 2 units in this direction. 1, 2. There you go. So 3 minus 2, and then minus 2 in the z-axis. So we go downwards instead of upwards. We go downwards. How many units? 2. 1, 2. I'm exaggerating, okay, because I want the drawing to look good. And so right there is where my point P2 is. There you go. So this is point 1, this is point 2, and this is how you draw them. And what about now needing to get the distance between these 2 points? Okay, I'm gonna draw the segment that joins them. I hope I can get it right. There you go. So point 1 and point 2 are joined by this segment in space, okay? And so how do you find the distance between point 1 and P2? And how do you find the middle point between point 1 and point 2 in space? We're talking about now in space, where my coordinates have, I'm sorry, where my points now have 3 coordinates. Well, the extension is very natural. The extension is, maybe you're guessing right now, the distance between point 1 and point 2 will be pretty much the same as before. But now we're gonna add the following. Look, before the distance looked like so, right? For points in the plane. And now for points in space, we only have to add or include the z component. like so. Okay, that's all we have to add, guys. This is uh, the new guy, the new inclusion. Okay, this is the distance between 2 points that belong in space. There you have it. And also the formulas for the middle point. If we assume that the middle point is over here, middle point or middle point, and it has coordinates xm, ym, and zm, then these three coordinates are given as before by the following. Xm is going to be equal to x1 plus x2 over 2. Ym is going to be y1 plus y2 over 2. And zm will be equal to z1 plus z2 over 2. Okay, and in all of these formulas, what does x1, x2, y1, y2, z1, and z2 mean? They mean the coordinates of my points. You see, it's the extension of the formulas. Extension to three-dimensional space is very natural. We just have to add this thing here and this new formula. And that's it, guys. I don't want to entertain you anymore. That was a very long class. And now get to solve the exercises. And that's it. Thanks so much and have a great weekend.